Hey everyone. Oops. In this video I'll be talking about the center of pressure. Okay, so first I'm going to go over a little nomenclature first, and then go to what the center of pressure actually is for an airfoil. So up here to the left I drew a simple airfoil, and in the red is the pressure distribution around the airfoil, just an arbitrary pressure distribution. And the pressure varies as a function of S, where S is the distance along the surface, so really it's just where you are on the surface. So you can see that the pressure is varying based on what S is, essentially. Okay, so this is an airfoil, and you can see that this green line going from the leading edge point to the trailing edge point, that's the length of this line is the chord. And over here we have the free stream air coming in, so that's V infinity. And I extended this chord line out with these dotted lines, and the angle between the chord line and the free stream velocity is the angle of attack. The angle of attack doesn't necessarily have to be the direction. Is not the angle between the chord line and the movement direction. So like if the airfoil were actually moving down this way, and the V infinity was still coming horizontally across, the angle of attack would not be the angle between the chord line and the movement direction. So it's always between the free stream air hitting the airfoil. Okay, so and then now we can look at a certain resultant force acting at this point on the airfoil, and so that's the R vector coming up here. So we can break it up into components. I'm going to break it up first into components that are perpendicular to the incoming free stream air, and tangent or parallel to the free stream air. So the component that's normal to the free stream air is the lift, and the component that is parallel is the drag. And then if we look at the chord line, we can break up the resultant force vector into components along the chord line. So perpendicular to the chord line is a normal force, and parallel to the chord line is the axial force. Okay, and then here's a little sign convention for moments about an airfoil. So we're going to be talking about the moments about the leading edge of an airfoil. So these are two different airfoils. If the moment M leading edge, so M sub LE, is giving you a positive angle of attack, so increasing the angle of attack, then we call it a positive moment. And the negative moment is when the moment tends to rotate the airfoil nose down, so pitch down. Okay, so the forces that are acting on an airfoil are the pressure forces and the shear stresses. So the forces and moments on an airfoil come from just the pressure variation, which is this red, and the shear stress distribution, which I haven't shown, which is due to friction. And these forces act tangent to the airfoil surface. Okay, so if we take those forces, or we take those pressures and shear stresses and integrate them over the airfoil, you can end up getting a moment about the leading edge, which for cambered airfoil, positively cambered airfoils, ends up being negative, but it depends also based on what the airfoil shape is, but I just described it as a negative moment about the leading edge point here. Okay, so the question to find the center of pressure is what R component on this airfoil, somewhere on this airfoil, or R vector, with components of the normal and axial force, will give you this moment that was generated from the overall pressure and shear stress distributions on the airfoil. So what I did here is I just took the airfoil and I put some normal force and some axial force. So the same way, so the axial force is acting along the chord line, the normal force is acting perpendicular to the chord line, and put it at some distance x center of pressure away. So that's the distance of the center of pressure from the leading edge. And then here again is the leading edge moment, the negative leading edge moment that was generated from the distribution of the pressure and shear stress over this airfoil. So what we're trying to find is what is the XCP, and so what you can do is you can say so essentially we can take a moment, or say that this is the moment about the leading edge, and we want the normal and axial force on here to be equal to that moment. So what normal and axial force components here along this airfoil will give us this moment, and that's a simple balance. So you can say that the negative MLE, so the negative moment about the leading edge here, is equal to, and then we can take the moment about the leading edge using the normal and the axial. Since the axial is along the chord line, it has no contribution to the moment, so it's only the normal force here acting at a distance xcp away from the leading edge. So that's why, and it's creating a nose down moment, so I have negative normal force times xcp, and these are just the units down here. So the moments are in Newton meters, and the normal force is in newtons, the xcp is in meters. So what the center of pressure is actually, is the point at which the resultant of the distributed pressure load effectively acts. So you can describe the full pressure, shear stress field of an airfoil by just this normal and axial force here. Another way of putting it is that it's the point on the body about which the aerodynamic moment is zero. So when I draw the final airfoil, I can say that the final pressure shear stress distribution on the airfoil is given by this resultant force here acting at an xcp away with no moment on the airfoil. It's kind of like analogous to the center of gravity, where if you have some arbitrarily shaped body, if you take the integral or take the moments of every single little particle of mass inside of this eraser, and you take the summation of like the moments, the point about which the moment of the whole body is zero, that'll be your center of gravity, and that's effectively where all the mass acts in this body, and that's kind of the way that the center of pressure works. So an important thing to know about the center of pressure is that it moves based on a changing pressure field. So if you have an airfoil and it's flying level like this, you have a certain pressure distribution, and you'll have a certain distance away from the leading edge, xcp, where the normal force acts. If you change the angle of attack, your pressure field is going to change, which means that your resultant force is going to act at a different distance away from the leading edge. So as you pitch your airfoil, you're going to have the xcp distance is going to either move forward or backward, depending on whether you pitch up or down. And that's not really that great for describing, for stability purposes, and for trying to describe the stability of a plane or a wing. So what they do is they use something called the aerodynamic center instead, and I'll go over that in a different video. Alright, thanks for watching.